Did you know that the meaning of geometry can be found in the name? If you look into geometry, you've got geo and then metry. Geo refers to the same thing as geology, which is the earth. So you've got earth and then you've got metry, such as trigonometry or any other kind of metry, which is going to be your metric, in other words, your measurement. So geometry is really just earth measurement, which makes sense that geometry was the first mathematics that was formalized and studied by mathematicians, apart from counting and simple arithmetic. Now, this is a time way before the math that we know today. Numbers were still Roman numerals. Most of the time they were just ticks on a bone or on a stick. Sometimes when you had more advanced civilizations like the Egyptians, then you had symbols to represent numbers, but most of the time you had a picture that meant 10, not a digit. Now, I want to show you how amazing this process of being able to tie in numbers and pictures was, how powerful geometry was, but also its limitations and why it is that most of the time today when we want to solve problems that involve numbers, we're not usually reaching for shapes, we're usually reaching for algebra, which is why we study it here. So let's take a look at a difficult problem, and let's see how much different it is to handle this problem when you're talking about it with geometry versus when you're talking about it with the power of algebra. So here's the question I want to look at. Let's imagine that we have the question x squared minus 6. So I'll put this in. We got x squared minus 6x equals 16. Now what we mean by this in today's language is that we're looking for values of x that are unknown, but that cause all of this to come out to be true. So we're looking for solutions. Now let me show you how this would have been interpreted back in ancient Greece, circa 300 years before Christ, when math had been formalized and when some of the greatest equations that we know today, such as the area of a circle, such as being able to find out the volume of a sphere, or how to form a parabola, how to track the heavens, and how to navigate across oceans and across bays. All of this came about in time way before being able to move x's around, or in fact even representing things with x's at all. Instead, they would handle the problem a little bit like this. First, they'd need to recognize that this problem could actually be written as two separate problems. The first problem could be written as where you have x minus y equals 6, and the next problem could be written as x times y is equal to 16. Now this might seem kind of crazy. To me it does. I don't understand how it is that these would be the same or how you would recognize that these are the same, but there's a really quick way for us to check that they are the same. So for example, what could we do here? Perhaps maybe I solve for y and I say y is equal to 16 divided by x. That'd be if I divided both sides by x. And if I plugged that into the other side, that would be x minus, and instead of y I could put 16 divided by x equals 6. And then I could multiply everything by x to hopefully get rid of that denominator. That would be x squared minus 16 equals 6x. There you go. And then by subtracting 6x from the left and right, and by adding 16 to the left and right, you would be able to get our original problem. X squared minus 6x is equal to 16. So that's kind of crazy, first of all, that you could even recognize that one of these problems could be thought of in two separate problems. So that was the first step that geometers had to be able to recognize, and they had to be able to recognize it like this, because this problem itself is very, very difficult to represent in pictures otherwise. And I'm about to take you on a whirlwind, so see if you can hang on tight. If you don't want to take notes, you don't have to, but I think you're going to find it very interesting, even if it's just a fun little trivia fact. So here's how the problem would normally have been interpreted. It'd be find two numbers, x and y, whose difference is 6 and whose product is 16. And notice that that's what we're talking about right here. The difference is 6 and whose product is 16. So we're saying if we solve this problem, we've really solved the original problem. And so what we would first want to do is we would want to draw a rectangle that has these side lengths, okay? So here we are, we're going to draw this out. We've got one side that is x, and we have another that's going to be a side of y, okay? In fact, actually, let me go ahead and put the x over here on the top. We'll put x here. We'll put y over here. And so what this means is that if I want their difference to be 6, then that means if I take a little length here and I kind of bring my y string around, or my y ruler around, then that means that all of this remaining length here has to be the difference. This has to be a length of 6. So you could think of that as being this length to this length all the way through is 6. This is the picture version of finding out two numbers whose difference is 6. Okay? Now we need to find out that the product is 16, and we know that that means that x times y is going to be 16. So on the inside, what we have is 16 units. That would mean that this thing in here would have to be 16 units large. That's exactly what it means to have x times y in the same way that we've looked at it from before. So if we now transform this rectangle and we combine it with a square, recognize what we can do here. I'm going to be very strategic about this, where now instead of looking at it as 6, I'm going to look at it as a length of 3 and a length of 3. So let's go ahead and clear this out. And if I imagine taking and picking up this picture, I could rewrite this entire picture as my y by y square here. I could have my 3 by y square come here. I could put another 3 by y square here. Or rectangle, excuse me. So here I have something that is a length of 3, it's a height of y, this is y by y, which gets me my original y squared, and this gets me another 3y. So here we are, we're using just our simple lengths, and we're trying to manipulate this until I can get to some kind of resolution. We're just playing here. Well, I could recognize that perhaps I would use what I have in front of me to make a square, so I could make this into a square. And so what I'm really representing in all of this using today's language is that if I have my y and 3, my y and my 3, and down here, small typo here, this should be a length of 3, this was a width of y, there we are. And so here I have another y and 3, so this is my entire shape would be a y plus 3 square, a square that is made from y and 3. That would be this shape right here. So my yellow is going to be my y plus 3 square. And what I know is that really what we have written here is all of these 16 units are taken up here, here, and here. So that's going to be 16 units. And I know that the missing part right here, what I would need to complete this square, would need to be 9 more units. So what I can say is that this entire big square is 16 and 9. Kind of cool that we're just playing around with this here. So now I've kind of taken one picture and taken things I could draw with a ruler and a straight edge, and I've moved it around until I'm able to get something that just describes my y. So I went from something that had a picture of x and y to something that just has a picture of y, and now I'm going to try to take that further to where I can actually get a conclusion here. Okay, so the last little thing that I'm going to try to do, if I'm playing around in geometry land, is I'm going to try to find some way of expressing that I have this y plus 3 square equals my, well, this could be thought of as a 4 square, and this could be thought of as a 3 square. Now, if you've ever seen a square plus a square equals a square, then you're ahead of me, because the equation that geometers were most familiar with back even into the ancient days was that of the Pythagorean theorem. So in other words, they recognized that this looks very similar to c squared being equal to a squared plus b squared. So now again, we've recognized that we could represent this as another picture. We could think of this as a right triangle whose hypotenuse is y plus 3, who has one leg that is 4 units long, has another leg that is 3 units long. Okay. What can we do from here? Well, from here, what we could consider is that if I was to take my little y plus 3 side, and I was to draw it as a circle where I brought it all the way down to the same line as here, that would mean that, similarly, I would have to have, oh, excuse me, there's one more step that I almost missed. We could actually have solved this out. So we could look at this as saying, if I'm looking for 4 squared and 3 squared, 4 squared is my 16, 3 squared gets me my 9. Altogether, this gets me my 25. 25 is a 5 square. So lo and behold, we've actually found out that this y plus 3 has to be 5 units long. Well, if y plus 3 has to be 5 units long, that means that y has to be 2 units long. So here we are, we found one of our numbers. And I could just as easily figure out how big x is, because I know the difference between them is going to be 6. So here's what I'm going to do. I'm going to try to draw out exactly what it is that I need to have for my kind of space here. I've got y plus 3, which is 5, and I'm going to draw that down here in my circle, what I was trying to do before. So that gets me a total of 5 right here. That is only 2 bigger, or that would be, let's see, I have 3, oh, there it is. I have my y equals 2, so that means this is my length of 5. Okay, so that means that this has to be my little y here, this has to be y equals 2. That's perfect. And then if I am trying to figure out x is 6 units bigger, and so if I wanted to kind of think of it as saying I have 3, I have my y equals 2, and I need 3 more to get my x, maybe I just draw another length of 3, and then I could say that this entire stretch right here would be my 2 plus 6 equals 8. And that's how geometers used to sketch this out. It's a little bit crazy, but if you take a look at it, what we've really figured out here is that if I go through all of this effort and I take y and I relate it to x and I get it into a rectangle, and then I rearrange that rectangle so that I can get another pattern that I'm familiar with, and I can use that other pattern to get another pattern I'm familiar with. And if all in all I'm just simply looking until I finally have a breakthrough where I say that y is equal to 2, and if y is equal to 2, and I want to grow it by 6 to get to my original problem, then that means that I can grow it by 6 to get something that's 6 units longer. That gets me 8. That would be x equals 8. And what we'll find out is that this is actually the same way that it works with this original problem. Let's try it out. X equals 8 would be 8 squared minus 6 times 8. If I simplify that down, 8 times 8 is 64. Minus 6 times 8 would be 48. 64 minus 48 would indeed be 16. And so I found the solution to my original problem. That's the power of geometry. Very, very strange that you are tackling such large and abstract problems as this, using nothing but shapes and familiar patterns, like the idea of a square and the idea of a triangle. Now, all of this is not something that I want you to know how to do. It's not something I want you to have to know how to recreate. It's just something I kind of want to show you, and I want you to be able to kind of appreciate it. Because what I want to show you instead, and what I want to encourage us to do, is to instead look at algebra. So historically, geometry owned mathematics for hundreds and thousands of years, until in the Middle East, algebra began to be studied. In the Middle East and India, a new pattern of representing things that were unknown with either boxes or x's began to emerge as a simpler way to find these unknown patterns. And it took the rest of the world an additional couple hundred, if not 1,000 years to get comfortable with transitioning from this broad expanse of notations using pictures and geometry and things people could see to algebra, which is a lot more abstract, but allows us to get to answers much simpler. And so let me show you how we would solve this exact same problem we started with using algebra. Using algebra, we would say x squared minus 6x equals 16. Could be rewritten as x squared minus 6x minus 16 equals 0. And I could think about this as saying, well, I'm looking for something that's going to multiply to my x squared. That would be x and x. I'm looking for some two numbers that will multiply to 16. That could be 1 and 16. That could be 2 and 8. That could be 4 and 4. But they need to add up to negative 6. Ah, well, that's because it needs to multiply to negative 16. So I could think of this as being a negative plus or minus 2, or a negative or positive 8. And lo and behold, we find a little bit of playing with our answer. We know that 16 is going to be multiplied to, and negative 6 is going to be added to, when I have x minus 8 and x plus 2 equals 0. That means that individually, x minus 8 could equal 0, x plus 2 could equal 0, which means that x could equal 8 or -2. Take a look at that. That's the power of algebra. And there's definitely ways where we can go back and we can relate this problem to geometry, and we can use geometry to help us think about how is it that I might be able to represent factoring like this. But overall, all we're doing is using the properties of addition, subtraction, multiplication, division, and our own logic to rearrange things so that we can abstractly come to what are these missing solutions. Now, as you can imagine, and as I described, there was quite the rift that occurred in mathematics between geometry and algebra. Talking about things as shapes versus talking about things as equations were two completely different tools that mathematicians used. After all, if you wanted to talk about a circle, you would go and you would consult with the geometricians. You would go and consult with that field of mathematics. If you were trying to find numbers that were needed to solve your problem or to help you balance out your checkbooks, that would be the ones that you would go to the algebraists for, and you would ask them for their assistance. But all of a sudden, in about the 1700s, I believe it was 1700s, let's take a look here. A gentleman by the name of Rene Descartes, he was doing nothing more than sitting in his bed, staring at the ceiling, when he would cause these two worlds of mathematics to collide. So here goes the story. First of all, Rene Descartes was a philosopher. He was somebody who you may be familiar with as having coined his phrase as I think, therefore I am. That's maybe his most famous contribution to the world. However, in addition to being a philosopher, he was a mathematician. And so, as a mathematician, he was often thinking deep thoughts and trying to connect abstract ideas. And he was known to like to lay in his bed and sleep for quite a while into the day. And even into the afternoon, he would lay there staring at his ceiling and thinking. And it was one such day that he recognized that he could describe shapes and he could describe algebra using a common tool. And so the story goes like this. While staring at his ceiling, Rene Descartes saw a spider, and the spider was climbing across the ceiling. And he had an old-style ceiling that had corners of the room, and in between corners of the room he had a decorative ceiling that had lines, grids, squares, all across it. And it was while he watched this spider move across that he recognized that he could describe the location of the spider at any given moment as how far away it was from a given corner. So he could describe this spider as saying that it was approximately 2 squares to the right, and it was approximately 3 squares high. And that by giving this spider an identifier by saying that it was 2 across and 3 up, he was able to tie numbers to a position in space. And that as that spider moved around, he could create equations that talked about how this spider was moving from one set of numbers to another set of numbers. This one would be 1 comma perhaps 3.5. I think this would be better as a 2.5, and this would be better as a 3. And that if there was a way to identify what this pattern was, he could write it as an equation. And that if he could connect where the spider was at any given time, he could get a picture just like all those studying geometry. Now this is a very novel idea, a very ingenious idea, one that revolutionized mathematics not a long time ago. And I want to show you today exactly how we use this all the time in modern day mathematics. So let's explore as Rene Descartes did on his first time. And let's imagine that we were starting off with an equation that came from the algebraists, this y equals x squared minus 4x plus 4. And we wanted to try to figure out what's the picture, what's the hidden picture behind this equation? Well, we could start off the same way that Descartes did. We could draw our ceiling, but this time maybe we want to step our ceiling out a little bit. So now I have not only some positive steps that I could have in my up direction, and some positive steps I could have in my sideways direction, but perhaps I want to consider also some negative steps. So this would be my negative step area over here, and I would have some negative heights, or I could have some dropping below my corner that result from here. So what we're going to try to do is we're going to try to separate these sideways and up and down, since they are, well, two different ideas here. And so we could connect one of them with x, our inputs, and we connect one of them with y's, our outputs. And thus I can sort of ask questions like saying, if I put in something for x, what's the picture that emerges after I figure out y? And that's going to have positive values, negative values, etc. So over here, we can think of these as being the negative values. These are going to be your positive x values over here. And this is similarly going to be your positive y values and your negative y values. And we'd like to sometimes talk about this a little bit more in detail by talking about what these quadrants are. And so we'll just label them the same way that we explored them the first time. We'll call this quadrant 1. Quadrant 1 will be the simplest version, where I have stepping over 1, 2, 3, my positive numbers, possibly fraction numbers and decimals as well, but my positive x values. And then I go up my positive y values. So this will be quadrant 1. And then I guess the next one would be, well, what if I was to input negative values for x and figure out what that occurred? That would be quadrant 2, where I have negative x values being entered, and I would be getting out some positive y values. But I guess I could also have negative y values, so we'll call that quadrant 3. That'll be where I have negative x's and negative y's, and then we'll call this one quadrant 4, just to kind of keep the pattern up. So you've got this kind of clockwise or counterclockwise rotation that we're creating as we're labeling everything. So if I say quadrant 2, now you know exactly what we're referring to. We're talking about the top left portion of this coordinate plane. And sometimes you will hear this referred to as a Cartesian coordinate plane. So Cartesian, to come from Rene Descartes, it's named after him. Descartes, there we are. So Cartesian coming from Descartes. Okay, enough playing around. Let's see, or enough of the setup. Let's see if we can get into the actual playing around. What is the shape of this graph? Well, if I was to draw my coordinate plane, my Cartesian coordinates here, I would ask myself, well, what happens if I put in an x value of 1? And so we could do a little bit of work here. If I set x equals 1, then that would be when I put in 1 and I square it, I put in my negative 4 from the original problem, I multiply that by 1, and then I add 4. That would get me 1 squared is 1, minus 4 times 1 would be 9 is 4, plus 4. So all in all, that would get me a value of 1 that would be equal to my y value. So what I found out is that I can kind of have this pair, this ordered pair, that starts off with having x equal 1 and gives me y equal 1. So that means if I take one step in my x direction, I could take one step in my y direction, and I could put a dot there. And I'll label that just so that I understand what I put in first and how I got that out next. So I'll say that's going to be the result from putting in 1 and then getting out 1. Kind of interesting. So next thing, let's try another value. Let's try if I have x equals 2. If I put in x equals 2, if I put in x equals 2, then that's going to be where I now am having 2 squared. So I have 2 squared, and then I'm going to be subtracting 4 times 2. And then I would be adding 4. So all in all, what would that get me? 2 squared is 4, minus 4 times 2 would be minus 8, so it'd be negative 4, and then I'd add 4 back, so that would give me a total of 0. So now I've got a new coordinate. My new coordinate says that if I put in an x value of 2, so now I go over 1, 2 in my x direction, that I need to go up 0. So I'll just put a circle here, or a little dot here, right at the value for going over 2 and up 0. Kind of nice. Let's try a few more. Let's see exactly what the shape is going to be. Let's do x is equal to 3. And if I plug in 3, what is that going to get me? X is equal to 3 would get me 3 squared, which would then get me minus 4 times 3, which would be minus 12. And then I could put in plus 4. So I've got 3 squared is 9, minus 12 would be a negative 3, plus 4 would be equal to 1. So it looks like as I come over here to my 3 and I look for where's the spider happening, again I've got another ordered pair where now I put in 3 and I've gotten out 1. So it's almost like this spider is taking a path where it started high and it went low and then it's going back high again. And you could do this for in-between values as well. Put in 2.5. You could do this for negative values. We could put in x is equal to negative 1 and see what that happens. That would be negative 1 squared. I'm going to put it in parentheses because I have to square the whole x value. So I'm squaring negative 1, and then I'm doing negative 4 times negative 1, and then I'm adding that to 4. And so that's going to get me negative 1 squared is 1, minus 4 times negative 1 gets me a positive 4, and then adding another 4 at the end of that gets me a y value that's 9. So that says that if I started with an x value of negative 1, I went backwards 1, I would need to go up 9. 1, 2, 3, 4, 5. That's really high up there. 6, 7, 8, 9. We'll put something all the way up here. And all in all, what I've gotten as a description from this is the shape. If this describes the pattern of my spider, now I can see what that actually looks like. It's going to be all values, a nice clean curve that connect these dots all the way on through. And it's actually a shape that we call a parabola. We've seen it before. And it happens every time we start with y equaling a quadratic. This is a shape that pops up not only when you're talking about the movement of the stars, but also the movement of subatomic particles. It's actually something that refers to, or that comes up in electricity. It comes up when you're talking about how things move with magnetism. In addition, it's also one of the few shapes that you can use to concentrate sunlight. That helps to be used whenever you're working with satellite dishes and trying to pull in information for technology. And it's also something that Archimedes, back thousands of years ago, reportedly used to help create what he referred to as heat rays or death rays, to be able to fight off incoming warships and burst them into flames before they could ever get close to his coastal village of Syracuse. So a really, really interesting shape. Sundials, it comes up everywhere. It's really, really awesome. But that's the shape, the parabola that it comes from, looking at this equation, this algebraic equation. Now I can see the math. I can see visually a shape that means an equation. That's an absolutely wild idea. So let's take a look at this one. What do we think is the hidden shape behind this one? X squared plus y squared equals 1. Well, let's try some values. I'm going to try, I'll draw my coordinate plane, and I'll try some values. Maybe I'll try x equals 0 first. That seems to be a nice easy one to start with. That would be, then I put in 0 and I'll square it. I'm be adding it to y squared. I don't know what y is yet. I'll have to figure that out, but that's equal to 1. Well, 0 squared is 0, plus y squared would just be y squared equals 1. And if I get rid of the square, that would be if I did a square root on both sides. Correction. You get rid of a square by doing a plus or minus square root on both sides. So that would be y equals plus or minus square root of 1. And the square root of 1 would just be 1. So that'd be y is equal to plus or minus 1. Now this seems kind of weird. That means if I put in an x value, I could get either a solution at positive 1 or negative 1. How would we draw that? Well, I'd go 0 steps over, so I would still be right here at the center, and then I would go 1 step up, and that could be one of my points. My points, my little coordinate or ordered pair would be 0, 1 to show that I did 0 steps to the left or right, and that I went up 1. And then I could do another one where I go 0 steps over and I go down 1, and that would be my other ordered pair. That would be 0, negative 1. So those are two different points that are both going to be solutions to this original problem. And you can try that. Try to type in x equals 0 and put in y equals positive or negative 1 into this original equation, and you'll see that it's going to work out on the left side as the same in the right. Let's try some more. What's this shape? Is it just these two dots? What if I try x equals 1? That would be 1 squared is 1. Plus y squared equals 1. I could subtract 1 from both sides. That would get me y squared equals 0. And then I could positive or minus square root both sides. That gets me y equals plus or minus square root of 0. But I guess that'd just still be 0. So I guess this one only has one answer that happens when I plug in x equals 1. That would be when I take 1 step over here to the right, I would go up nothing. So here we are. That would just be a point. And that would be at the point I put in 1 for x, and I got out 0 for y. Let's try another. Let's put in x equals negative 1. X equals negative 1 would get me negative 1 squared. Make sure you square the entire thing with parentheses. Plus y squared equals 1. And negative 1 squared is just 1. Plus y squared equals 1, which means that y squared has to be equal to 0 again. So again, y equals 0. So it looks like if I take 1 step over here to the left, that's going to be where I am at x equals negative 1. And y is equal to 0 again. And so that's going to be another point right here. What is this shape? What do we think this shape is? Well, I'm going to show you one way that you can look at this one. If you remember, like in our introduction, here, look for those patterns. They appear in some of the strangest places. And here you have a square, you're adding it to another square, and you get another square number. And I could rewrite this and say that it looks very similar to the structure a squared plus b squared equals c squared. It's a triangle. It's a right triangle. It's a right triangle whose hypotenuse is always 1 unit long. So what we have here is an expression, an equation, that captures every single triangle that can be drawn that has a hypotenuse of 1. So that could be a hypotenuse of 1 here, that could be a length of 1. I could put my 1 here, 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 I could put my 1 up here. I could do all of those. And so what's the shape we get? Well, it's always the point that's creating those little triangles. And if we connect all of those points, what we'll find out is that we actually get a circle. This is the equation of a circle. And that's absolutely wild. If you imagine again, the geometricians all looking at this and going, but a circle is a shape. It's something I draw. I take a center and I use a compass. I make strings. I use rulers. I draw. This is a circle. And the algebraists are going, what are you talking about? This has nothing to do with a circle. This is just numbers that happen to work to equal out on both sides. This is just about solutions. But if you are creative and you allow yourself to model your logic and not be victim to the rules and constraints of everyone around you, there's nothing to say that this is any more of a circle than this one is. They both capture the exact same ideas, and I can connect them so long as I'm willing to change my perspective and model things a little differently. It's amazing that this is the equation for a circle. Now you can think of intercepts as being nothing more than how you would contextually hear things out in the real world. If you were talking about trying to intercept something like a flying object, you'd probably be talking about trying to throw something at it or get in something's way. And this is exactly what we're talking about when we're talking about intercepts of a graph. So here we are back again trying to draw out our ceiling, our extended infinite ceiling that Descartes originally had. We're going to refer to this again as our coordinate plane, where we have an origin, and that's a good vocabulary word for you. The origin is going to be at the very center. So we're going to say our origin is going to be this originating corner. You can think of it as a corner for our ceiling here. Now, when we're talking about intercepts though, intercepts of my graph would be whenever my graph is crossing a certain thing. So I could think of it as crossing these axes. So for example, let's draw some kind of nice squiggly shape. We'll call this some kind of curve. And so this is going to be my geometry, the little path that my spider is following. And my intercept is going to be when I cross something that is standard, that's important. So my y-intercept, for example, is going to be right here. This is when I am crossing, when I am intercepting my y-axis. Similarly, my x-intercept is going to be right here. This would be my x-intercept. Now we may want to describe this as a certain number of x value and y value in the same way we've been doing it before, but what I'm going to point out to us is that actually we don't need to think about too much when we're using these two problems. There's only small bits of information that give us everything we need. So y-intercept is the, let's see, blank of a point where a graph touches or crosses the, well, we know it's the y-axis because it's the y-intercept, so we'll say the y-axis. And it's the what of a point. Well, up here, what do I know? Do I know how high it is? I don't. I don't know exactly what the scale is. I don't know how curvy this curve is. Do I know how many steps over to the left or to the right or to the left that I've taken? I do, in fact. I've taken 0 steps. I'm still back at the beginning. So if I've taken 0 steps to the right and 0 steps to the left, and that's going to be true anytime I cross this y-axis, then really I don't care about the x value. I already know it. I always know it. My x value will always be 0 at my y-intercept because it's the only way for me to cross my y-intercept is to have not taken a step to the right or the left. Okay, so what am I really looking for? The y-intercept is going to be the y value. It's the y value. The y value of the point right here, where the graph touches or crosses the y-axis. Okay? The x-intercept, similarly now, is going to be the x value. Let me clear that away. X value of the point where the graph touches or crosses the, well, for the x-intercept, it would be crossing the x-axis. And so our picture up here, we're talking about the x value that corresponds here, the number of steps I have taken, because I don't care about how high or how low I am. I already know that. I am nothing above the ground and nothing below the ground. I'm right at 0 for my y value. So I always know the y value at my x-intercept, and I always know the x value at my y-intercept. They both have to be 0. So that's pretty easy. Really, we're just talking about what's the x value that causes it to cross the x-intercept, or we're talking across the x-axis, or what's the y value that causes it to cross the y-axis. Not too bad. So let's find the x-intercepts. If we're trying to find the x-intercept, but we're trying to do it algebraically, then I'm not going to be starting with a graph. I'm going to be starting with some kind of equation. So I have a y equals maybe some x's. I could have y's over here. I could have a number of different equations, plus, minuses, divisions. Anything that has algebra in it would be considered an algebraic equation. So if I'm trying to find my x-intercepts, how could I do that? How could I find my x-intercept? Well, if we take our picture and we pull back to the numbers we were just describing, my x-intercept is going to occur when y is equal to what? It's when y is equal to 0. So I could think about finding x-intercepts as being whenever y is equal to 0. And the y-intercepts would similarly be, I'll leave that one for you. How would I find out where this y-intercept is? All right, so let's now take a look down here. Let's find the x and y-intercepts of the graph of the given equations. I'm going to find the x-intercept first. So if I want to find the x-intercept, that means I want to figure out when is my curve crossing that horizontal axis. When is it kind of dropping below that floor, if you will? Well, if it's dropping below the floor, then I already know its height. It's got to be at 0. So the height is going to be at 0. So if I'm trying to figure out the x-intercept, that's going to be when I set y equal to 0. And you could even write this all in one line. You could say y equals 0, and then you could write everything that y is equal to. There's nothing wrong with this way of saying it. 2x minus 1 over x plus 3. Pretty cool. Now, if I know that this entire fraction is equal to 0, there's a few ways we can think about this. The first way is if I want to get towards x, I could try to cancel out anything that's complicating me from getting to x. So here, for example, maybe I'm looking at this x as being the easy x to get to, and I want to get rid of my denominator. The denominator is nothing more than a number, and I can always get rid of a number by doing the inverse operation. So here, if I'm dividing by x plus 3, I could think of multiplying by x plus 3 to cancel that away. And if I do that on the right-hand side, I would have to do that to the left-hand side, which I guess here would just be that 0. I'd multiply by x plus 3. If this is getting confusing that I have the y equals 0, you're always allowed to erase this. Just because I can write something doesn't mean it's always useful to do so. So we could always just keep it like this and say I'm going to multiply the left side by x plus 3. Well, 0 times x plus 3 is just going to be 0. And then I have 2x minus 1 over x plus 3 times x plus 3. That's going to be dividing and multiplying by the same thing, so that cancels away to get me 2x minus 1. Now that's one way you could think about it. The other way you could think about it is that if I have a fraction, is there a number you could divide by that gets you 0? So for example, if the number on the top was 30, what would I need to divide 30 by in order to get 0? Now I hope you didn't say 0, because you can't divide by 0. 30 divided by 0 doesn't work. So it's not divided by 0. Is there a number that I could divide by to get me a 0? If I divide by 2, that gets me 15. If I divide by 3, that gets me 10. Those numbers are getting smaller. I could divide by 9,000, and that would give me a very small number, but not quite 0. I don't think there's a number here. So really what that means is that if you want to create 0, you need to find out when the numerator, the top here, is equal to 0, not when the bottom is equal to 0. So that's another reason why it is that we can look at it as, when does 2x minus 1 equal 0? Because if the top is 0, the entire fraction is 0. Kind of a different way of thinking about that. All right, so we're solving out for x. That's going to be, if I add 1 to both sides, that gets me 1, and then equal to x. And then I could divide by 2 on both sides. That gets me x is equal to 1/2. So all in all, we found out that at x equals 1/2, y is equal to 0. Remember, we start with y equals 0. This is the coordinate, the pair that goes along with it. So you can even think of that as a coordinate pair. You really are thinking about this here as saying whenever x is 1/2 in this pattern, y has to equal 0. So that would be also equal to our x-intercept. This 1/2 could be written as our x-intercept. Now, how would we do that to find the y-intercept? Well, this time instead of starting with y equals 0, we're going to put in x equals 0. So if x is equal to 0, it actually turns into a much easier problem. Throwing that in would be y equals, and then if x is 0, that's 2 times 0 is 0 minus 1 over 0 plus 3. So that would just simply be negative 1/3. So when x is equal to 0, y is equal to negative 1/3. Now, as we can see, this gets a little bit clunky to write out. So sometimes we like to write this a little bit simpler using commas. So we can write this as saying the x-intercept is going to occur at 1/2, comma 0. In other words, the x-intercept is at the 1/2 mark. And then we could say the y-intercept is going to be at the point 0, comma negative 1/3. In other words, the y-intercept is negative 1/3. Kind of fun. I'm going to leave it to you to try this one for B. Find out what the x-intercept is, and the x-intercept is going to be plugging in 0 for y. The y-intercept is going to be when we plug in 0 for x. And the reason is, again, going back to that curve. If you ever forget, draw yourself a little bit of a sketch over here and say, if I was going to cross here, if I was going to cross the x-axis, what's my y value? If I was going to cross the y-axis, what's my x value? And see if you can reverse logic it back to where you need. So let's now take a little bit back and see if we can't use all this coordinate to make this coordinate system to solve problems that might otherwise appear to be quite difficult. Let's try to find the distance between these 2 points. Can we do it? Well, we can if we start with trying to look at the geometry. So let's sketch it out. Let's sketch it out and put these 2 points here. Negative 3 comma 2 means I'm taking 3 steps backwards. So I have 3 steps backwards and then I'm going 2 steps up. So I'm going 1, 2, and then 3 steps over, and then I'm going 1 and then 2 steps up, okay? So that's going to be right here. And then from here, I need to go over to 4 comma 6. That'd be if I took 1, 2, 3, 4 steps to the right, and I'll put in a tick mark for each one, and then I'm going 6 steps up. So that'd be 1, 2, 3, 4, 5, and 6. Ooh, that's a long ways up there. Okay. So we're going all the way up here in order to find our next point. And so the distance I'm looking for is this distance. I don't know, that looks pretty challenging. Is there a way that we could use another picture to help us out? Remember that now the way we've combined the worlds of algebra and geometry, we can use anything we want so long as I can put it into this picture. Well, I'll tell you what I can find out. I can very easily, if I'm channeling my inner geometrician, I could tell you how long this is. This would be starting at negative 3 in my x value, and then going all the way until I got to a 4 in my x value. Okay, so that's a distance that would be, well, could we figure that out? Hold on, we could use the absolute values that we studied before to help us out with that. That'd be, I need to figure out the distance between negative 3 and 4, so it'd be negative 3 minus 4, or vice versa, 4 minus negative 3, and then absolute value, that'd be a 7, so I have a 7. Okay, so that's 7 here, that's my length. Nice, like that. Similarly, I could play around, and I know that I could explore this here. This would be the height that is going from 2 up to 6. So this would be absolute value of 6 minus 2 gets me 4. So I know this can be a height of 4. And I know that if I travel to the right, it's perfectly perpendicular to going up and down. I think we've created a triangle. Now, if you didn't see this as we were creating it, that's not a problem. Keep in mind that math is not something that we do, it's something we discover. It was said that, for example, what was it? Archimedes, one of the greatest scientists known to mankind, would spend hours in his bathing halls carving on the walls and speaking nonsense to himself until he came up with insight. He was playing. He would enter into fits that he believed to be almost euphoric spits of joy as he was discovering these riddles and seeing into the heart of the universe. We're doing the same idea here. We're just playing until all of a sudden something clicks, and then it makes it really hard to forget. So we've created a triangle here with numbers that were already available, and this triangle is a right triangle. And so lo and behold, couldn't we just simply use our Pythagorean theorem? A squared plus b squared equals c squared. Okay. Well, what's my a squared? That would be 7 squared. What's my b squared? That would be 4 squared. It'd be the other length of my my right triangle, okay? And then I'd be trying to find c squared. C squared would be the complete distance all the way at the top. That'd be my c, would be the distance, and I'm trying to use this with c squared. All right, 7 squared would be 49. 4 squared would be 16. C squared, I don't know yet. All right, and so that would get me 49 plus 16 gets me 50, 65 equals c squared, and then I could do a plus or minus square root on both sides. So that gets me plus or minus the square root of 65. And I could check real quick to see if 65 is going to factor at all and simplify. That would be 5 times 11, 12, 5 and 13. No, it's not going to simplify anymore, so that's about all that we've got. So c is going to equal plus or minus square root of 65. That means that this length right here is either positive 65 or negative 65. Which one do we think here is square root of 65? Which one do we think it is? Well, you better not say negative, because it's difficult to measure things as having a negative distance. The option we would need to choose here that was appropriate would be just the positive one. So we would say that after our little interpretation here, that we would need to make an executive decision, a mathematical decision, that based on the problem we were looking at, the correct choice between positive or negative root 65 would be the positive version. So we could say it's going to just be the square root of 65. And so that's the distance between these two. These points that just started as numbers, pairs, we could now relate them as having this distance, square root of 65. Now this feels like a lot of work if we don't take a moment and bring it back to a general formula that helps us to keep track of this for next time. So let's go back through and figure out how it is that we created this. The distance formula. Let's create the distance formula. What did we do? Well, we started with 2 different points, and instead of using numbers, let's see if we can keep it a little bit more generic. So we're going to start with, instead of an x value and a y value, we're going to write it in as an x value and a y value. X and y. Perfect. And we'll put a comma between them. Love it. And then I had another x and y value. So I'll write that one down as well. Oh, but I need to keep them separate. I have an x and a y, and these weren't the same x's and y's. Right now it looks like they're the same thing. So let's describe it. This will be the x value for number 1, point 1. I'll put a little 1 down here. And this will be the x for number 2. I'll put a little 2 down here. So I have x1, y1, and x2, y2. The x values for point 1, the y value for point 1, the x value for point 2, and the y value for point 2. Okay, perfect. What did we do next? The next thing we did, if I go back to look at my picture, I think we did this part next. We tried to find the length of the bases of those triangles, the legs there. How did we do that? Well, we took one of the x values, so we'll take, for example, x1, and we subtracted the other x value, and then we did an absolute value to make sure that we had positives only. Perfect, that got me one of the numbers right there. Then what did we do? We did the same thing with the y value, so I took y1 minus y2, and I put that in absolute values. Okay, so that got me my 2 numbers. What did I do with my numbers? Oh, I put my numbers into my Pythagorean theorem next. So then I squared both of those. Okay, so I squared both of those, and I added them together. And then when I added them together, that got me c squared. In other words, my distance. Okay, so I could put that in. I could put that in as my distance squared. Oh, but I don't just want distance squared, I want distance. How do I get rid of the squared? Well, we did that by square rooting both sides. So I could put a square root over both sides. And then that was what allowed me to cancel out with my little square here for my distance. And I don't even have to include my plus or minus, because I ended up getting rid of the minus part. That made no sense, and I was left with plus. And so this is what we've created, a distance formula. The distance formula is everything we have written down here. If I am given 2 points, x1, y1, and x2, y2, I can find the distance between those points by subtracting the x values, making that positive and squaring it, adding that to the y values once I've subtracted that, made it positive and squared it, and then square rooting both of those as if they were lengths of a triangle. This is how we connect geometry and algebra. It's a thrilling, fun example. It's a fun time. So let's do one last one before we call it. Can we find the midpoint between these 2 points? The midpoint. So again, let's go ahead and sketch this out. We sketch it out. I'm going 3 to the left and 2 up. 1, 2, 3 to the left and 2 up. 1, 2. I'll put a point there. And then I need to go 4 up. 4 to the right. 1, 2, 3, 4, and 6 up. So 1, 2, 3, 4, 5, 6 up. And that's my point right there. Okay, so I'm doing so far so good. And I need to find the midpoint. So now I'm looking for this halfway point right here. Whew, how can we do that one? This one requires a little bit of looking at for a while. But if you're patient, if you allow yourself, you might come to the conclusion that the halfway mark all the way up on this side is going to be the same as if I had one small triangle here, and I repeated that same small triangle here. So how long is this one? How long is this one? Each of those would be half of my original. So if I originally had my full distance along my x value as being 4 minus my negative 3, and then I need to make that absolute value, and then I'm trying to divide that by 2, now that would get me something like 7 over 2. I'm really trying to look at going this far over from one of them. Oh, I'm going 1, 2, 3 and a half would get me like here, and then I need to go up. That seems about right. So that's one option. Each of them is 7.5 away. So you could think of it as negative 3 plus 7 over 2 to get me from my original x value over to the midpoint. That would be fine. And then I could figure out what that would be with the y point in the exact same way. Half of the distance between 2 and 6 would be it'd be a distance of 4. Half of that would be 2. So then I need to go 2 plus 2, and that would get me let's see, negative 6 plus 7 gets me a 1/2 comma 4, and I think that might be right, because 3.5 more steps would get me to 4, and then if I went 2 more steps above 4, I would get to 6. I think that would work out just fine. I'll let you know there's a simpler way. What if instead I was trying to just find out that halfway mark between 4 and negative 3? Here's a way that we could do this, and this one again takes a little bit of thinking about. 4 plus my negative 3 divided by 2. That would get me 1 divided by 2 is 1/2, and then I have 6, and I would add that to 2 and divide that by 2. That would get me 4, and there we have it. A simpler way of getting to this midpoint formula isn't by just finding the distances, going back and forth and trying to add and subtract, although it's not a bad way to do it. It's by trying to find the averages. I'm trying to look at the average, and here's how we've recognized now the average is nothing more than the number that is in the middle of the two things I started with. Starting with 6, adding 2 to it, and then breaking that down into a half is the same as starting with one of these points and then going half the distance between them. That one's a fun riddle, and I'll leave that for you if it feels like those aren't connected. See if you can connect those in your head. But for the midpoint formula, we can think about it like this. If I want to find the midpoint, I'm going to take an x value. I'm going to add it to the other x value. So I'll call one x1 and the other x2, and I'll divide that by 2. For the y value, I will add one y value to the other y value, and I will divide by 2. And then that will be my midpoint. My midpoint will be when I take that many steps over to the left or right, and then when I take that many steps to the top or bottom, I will be halfway between each of the points.